An object is placed 95 centimeters from a concave mirror of radius 77 centimeters. Find the location of the image. Enter in centimeters. Use a negative number if the image is behind the mirror. And part B, what is the magnification of the mirror? Is the image real or virtual? Is the image upright or inverted? Select all that apply. So to explain this, I'm going to draw a little bit of a convex mirror right here. So here's my convex mirror, and then this is the center of the mirror, and so that squiggly line doesn't fit right in, but that's the center of the mirror. And here I'm going to place my object right here. It has so imagine now that this is my radius and that this is my focal point. If I draw a line straight out to the mirror, so some of the light's actually going to go straight out to the mirror, and it will come back and it will cross through the focal point. Then if I draw a line through the focal point, so some of the light will actually go through that focal point, and it will bounce straight backwards. And then some of the light will go down through the center point, and it will bounce and go straight back in the other direction. So the point where all three of these lines cross, that's where our image is going to be formed. And we call the position where our object was placed, we call that distance from the mirror, we call that P. And the position where the image was formed is Q. And so if you have any problems remembering that, just think of P as placement of the object and think of Q as quality image. It's where the image is most focused. And so we can use it's called the mirror equation. The mirror equation is 1 over Q plus 1 over P equals 2 over the radius. And so by radius, I mean if we had a mirror that was a sphere, if we cut that sphere in half, that would be our concave mirror. So the radius would be like right here. And so you could actually cut this at any point, and if light hit that, it would still act as if the radius was right here. In this situation, it actually gives us the radius, and so we can solve for where the image is going to be. We can solve for Q. So I want to isolate Q, so 1 over Q is equal to 2 over the radius minus 1 over the P. Now I simply need to take the inverse of both sides. Now you got to be careful. You can't just flip over these two fractions. One thing you can do is you can put a 1 over all of them, 2 over R minus 1 over P. The reason you can't flip these over is because, just by themselves, because there's not a common denominator. So this is one way around it, but then you have a complex fraction, so I don't like that method. The other thing you could do, 1 over Q equals 2 over R minus 1 over P. Put that all in parentheses and set it to the negative 1. That's the same thing. And both of these things I don't like because they allow for more calculator errors. And so what I like to do is I like to give it a common denominator. So 1 over Q is equal to, if I take this term R and multiply it by P over P, I get 2P over PR. And then I subtract 1 over P. Then I want to take this term P and I want to multiply it by R over R. So I'm multiplying both of these by 1 essentially, which means that it's not going to change the value. So I got 1 over Q is equal to 2 over P minus PR minus R over PR. Now I have a common denominator, and so what I can do is just simply say 1 over Q is equal to 2P minus R over PR. And I can just take the inverse of this term, and this is what I'm going to do every time. So I'll get Q is equal to P times R over 2P minus R. And since my answer is in centimeters, I don't have to convert to SI units. So I'm going to get 95 centimeters times 77 centimeters. Those are my P and my R, divided by 2 times 95 minus 77. You should get that Q is equal to 64.7 centimeters. Now part 2 wants to know the magnification, and so the magnification is defined as the height of the image which is h prime, divided by the height of the object, which is h. So the height of the image formed. Now what does this mean? So let me go back to the mirror that we drew. If I have an image that's let's say that's its height, then like we said, it's going to cross through. We have the focal point, we have the radius. If it goes straight, it's going to go down through the focal point. If it goes down through the focal point, it's going to bounce straight off. Anywhere these lines cross is where my image should form, and so it's now my image is upside down, and it's somewhat, it could either be smaller or it could be larger. And then if you wanted to check yourself, you would draw your line down through the radius, and it should cross at the same point, and it will bounce back in there. So it should cross at the same point, and it basically, I'm making it work here. But this height right here, if it's negative, it means that my image is inverted. If it's positive, it means that my image stays upright. So if my magnification is negative, it doesn't mean it shrunk it below 0. It means that your image got inverted, which in a way is kind of shrinking it past 0 and then going on further, but that's something else. But my height here, divided by the height here, is going to give me the magnification. That's the definition, but I don't know either of the two heights. But what you can do through some complex geometry is you get that the magnification is equal to h prime over h, which is equal to negative q over p. And since we just solved for q and p is given to us in the problem, we can just plug in our numbers. And what you're going to get is, for my numbers, is negative 0.68142 is the number I get. And it doesn't have units. Magnification doesn't have units because what you have is you have h prime in centimeters over h in centimeters, and the centimeters cancel out. So it's a unitless number. And since it's negative, I know that it's inverted. Then the other thing is, if q is positive, the image is real. If q is negative, the image is virtual. The q that we found was 64, positive 64, so we know it's a real image. But you think, what would it mean if it was negative? That would mean that all of my lines would intersect behind the plane of the mirror, or they would appear to intersect behind the plane of the mirror, which is something we'll see in a future problem. And basically what that's like is if you imagine that let's say our mirror is convex, and you had light bouncing off in this direction and light bouncing off in this direction, they would appear to come from behind the mirror if you continue the lines out, but in this case it doesn't. Hey, thanks for watching. Make sure you check out my blog. The link is down in the About section of this video. And on the blog, you'll find cool stuff like other videos for the same chapter. And you'll also find little download links where you can download calculators to basically just punch in your numbers and solve these exact problems. So you won't even have to watch the video if you don't want to. The last thing I want to say is if you leave comments on YouTube, of course I will get around to responding, but I'm much faster if you leave them at the bottom of my blog, right down there. Enjoy your day.